Velmi podporuji, že je mediálna tam byste řekli, já musím dodělat
Dobrý den, já vás vítám na přednášce z předmětu operační systémy a systémové programování. Dnešní přednáška bude taková atypická. Já jsem pozval kolegu Michala Hocka z firmy SUSE, který vám přednese přednášku o tom, jak vypadá reálný vývoj Linuxového jádra, jaké procesy tam probíhají, jaké nástroje se používají. Po dohodě s přednášejícím ta přednáška bude v angličtině. Vadí to někomu? Nevadí. Okay, so welcome on the lecture from the Operating System and Systems Programming course. Today I would like to present Michal Hocko, who will give you a presentation about Linux kernel development. He will make you familiar with tools and processes that are used while developing a real Linux kernel. So Michal, over to you. Just a little bit here.
Okay. Good morning, everybody. Thanks for introduction. And yeah, I'm Michal Hocko and I'm working for SUSE. And today I will be talking on behalf of both SUSE as a company, as well as Linux community at large, as I'm part of that community as well. The talk will not be very technical, but if you have any technical questions, then feel free to ask, of course. So what are we going to talk about? I will very briefly touch about on the topic of open source in general. Then I will be talking about how the upstream kernel development works and also how downstreams work. So before we jump into that, how many of you are familiar with open source in general? Okay, good coverage. How much or have you ever heard about Linux kernel in particular, or have you ever even tried to sign a patch or participate in development in any way? Okay, so not that much. Okay, so at least I have something new for you to tell. So open source, 1,000 feet look. Open source is much more about how the development works rather than any very specific business model. So in general, we're talking about open source when the source of the software is generally available. That might be not only available to users who are using that software, but also to developers who can participate in the project. Of course, the participation itself might be constrained. For example, you might be forced to sign contribution agreements or comply with a very specific licenses or copyleft or copyright rules. So open source project might be very much free, or it can also have some real constraints on participants. When we are talking about open source, probably the biggest advantage of the development model is that it encourages this decentralization. So it's really hard to own the project as such, as the source code is generally available. And that means that if you do not agree with the direction the project is taken, then you can fork that project and start developing it your own way. And then it, of course, a matter of who has the mass and development power to pursue any specific direction. When we're talking about open source, we are also talking about upstream and downstreams. So if we want to distinguish the two, then the upstream is generally the main line of the development. So it's where the stuff happens. decides directions. It decides what's acceptable, what's not acceptable, and generally has some power comparing to downstreams, which are generally following that development. As I said, that generally decentralized development has some advantages, but also some disadvantages. The biggest one would be probably the potential for fragmentation, where if you have hard time to align in a single way of development, then you might just fragment the development power and lag behind. The last thing that I would like to mention is that open source doesn't really mean a free software. A lot of people are just using those two interchangeably, but you can have pretty much a very commercial and successful project and have it open source at the same time. Why would you do that? For example, if you make your source code available, then you are more transparent to your users. They can see what you are doing, how you are doing that. You can encourage more auditing of the code for safety reasons or any other reasons. And also, many users might just realize that there are particular things that they might need that you are not providing yourselves, and they can contribute back by giving you essentially functionality that they would like to have. But that functionality being maintained by themselves in downstreams has some cost, obviously. The biggest one will be that the upstream project moves on and you have to constantly rewrite or rebase your changes on top of what's happening in upstream. So that encourages people to contribute back and have that functionality that they rely on moving along with the project. Yeah, so Linux kernel specifically, I guess it wouldn't be really exaggerating when we can say that the Linux kernel is probably the biggest open source project out there, with thousands of participants in every single release. The main and the only true upstream kernel is maintained by Linus Torvalds, and we also call it vanilla because it's clean. You can have a look and clone the Git repository where the main development happens. Or you can download tarbles that you can unpack and build without having that whole history that it's in the Git tree. Yes.
Just a question. Do you think that Linus Torvalds is himself managing the...
I will get to that at the very next slide, but the general development is a strong hierarchical structure. So it's not that Linus is developing the whole kernel, and that would be simply impossible. We're talking about multi-million lines of code projects. So he's essentially mostly gatekeeping and making important decisions and mostly taking code that somebody else is writing. So right. So
himself.
yes. So but he's heavily relying on many maintainers of a specific kernel area. So for example, memory management that I'm personally participating in, or drivers of any sort of hardware you can imagine, architectures, network layer, USB layer, and he relies on many top-level maintainers that over time have proven to be doing or making good decisions and sending code that it's of a reasonable quality. So it's not really easy to gain that trust to become a top-level maintainer. It's quite easy to lose that that trust. So essentially, he's merging, or we call it, he's pulling merge requests from top-level maintainers. Those are pulling or merging changes from sub-maintainers, and developers or participants are mostly discussing with those different levels of maintainers to provide the code. If you want to have a look at what kind of Git trees there are, then you can get the list there. Don't be surprised if you see many of them, like dozens, if not 100. The development itself mostly happens on the mailing list, so no fancy GitHub or kind of work development that you might be used to from other open source projects. Kernel seems to be rather old-fashioned and rely on email. There are many that believe that email is dead, but I guess this is a kind of example where that doesn't hold. Yeah, so what kind of different roles do we have in the upstream kernel development? So as I've already mentioned, there are maintainers. They are responsible for a particular part, we call it subsystem of the kernel. In many cases, or it's preferable if we have multiple maintainers driving a particular subsystem, because you can imagine that, or I'll show some numbers later on, but this is a task that is beyond a single person to manage. For example, in memory management, we have dozens of maintainers who are very in many cases, they're focusing on very specific parts of the memory management, because nobody can understand and wrap their head around the whole thing. Then we have reviewers. That's very close to being a maintainer, but maintainers sometimes have wider responsibilities. For example, keep track of changes that people are proposing, or managing their Git trees, while reviewers are mostly interested in watching the mailing list of their interest. And when somebody proposes a change, then they are evaluating that change. They are providing a feedback for improvements, or pointing to problems, bugs, or stylistic issues. Then we have contributors, and those are generally people who are sending changes that they would like to become part of the mainline kernel. That can be hobbyists that have their fancy little driver, or that can be people who are fighting with a particular problem that the Linux kernel doesn't either support or doesn't really work optimally for their particular use case. Or that might be people paid by companies to implement support for a specific hardware, or cover specific use cases. For example, me personally, I'm probably involved in all those categories, because as a memory management maintainer, I take care of the memory with other people about memory management. I act as a reviewer very often, and also whenever we have a customer issue that needs to be fixed, then I'm participating also as a contributor. And we have testers. Those might be real people, or those might be automatic systems for continual integrity testing, for example, zero-day bot provided by Intel, where they have a large farm of large machines and they're constantly running build test or testing different configurations, or they are running a load of test cases and provide feedback to the mailing list. For example, when a larger patch series is sent, and in a couple of hours you can see follow-up emails pointing to for example, that it has broken a particular combination of config options. And last but not least, we have users, and those are probably the most important members of the community as well. One thing that it's really worth mentioning is that there is a very strong no regression rule, and I mean it like very strong. That means that you might be proposing a change that makes a lot of sense, and but if it breaks somebody, then you have to deal with that, or your change will get reverted. Yeah, question? So the question was how often that rule gets broken. Very seldom. There might be cases where, for example, providing a backward compatibility is no longer sustainable. For example, because the existing interface is inherently broken. And in that case, there are exceptions, but those exceptions are really, really exceptions. Much more often you can see that even just recently there was a discussion about a particular syscall that systemd would like to use for starting new processes, and that proposal makes a lot of sense, but it would have a potential to break users, so it had to be really abundant. So how the kernel development works itself. It might come as a surprise for a large project like the kernel, and something that it's used in so many different deployments, is that essentially this is a constantly rolling development model. So there is no particular feature plan. It's simply a very stable and predictable time-based scheduled development model. So we're starting with 2 weeks of merge window, or we call it merge window, and that it's time when all the aggregated work collected by maintainers and sub-maintainers is sent towards Linus, and he's merging, or as we call it, pulling those merge requests, and that's when the code becomes part of the upstream Linux kernel. As you, yeah, it's not waiting. So as you can see, for example, in the current development model, in the current development release, that it's 6.12, we have something like 225 merges done by Linus. That itself has brought something like 11,000 new commits into the kernel. I didn't do particular statistics about the number of lines of code because, yeah. But as you can see, for example, comparing to previous release cycle that was 6.11, the number is mostly stable. So that's what I call the predictability of the development model. So you cannot really assume a particular feature set in a release cycle, but you can rely on the stability of the whole machinery rolling. After those 2 weeks, there is RC1 released, and since then there is a weekly based release of release candidates up to usually and including RC7, sometimes even RC8, depending on how many changes are merged during that time period. And as you can see, for example, all the commits that were merged since RC1 until 6.11 final release, it's something like 10 times less than the number of changes that were released during the March window. And again, that's kind of stable comparing to previous release cycle. I do not have anything for 6.12 because we are currently at RC2. So it's 5 more weeks to go to get final 6.12 release. During this time period, Linus really enforces that he would like to get mostly bug fixes or stuff that it's that is either obvious or fixing pre-existing bugs or bugs that were introduced during the merge window. So no new features. And if something gets broken and author of the change is not really responding or fix might be too complex, then there is a aggressive revert policy. So getting something into Linux tree doesn't really mean it stays there. Final release, when RCs are released, Linus usually write an email summarizing what has been merged during the last RC, and he indicates his kind of gut feeling about number of changes that were merged, what kind of those changes were, and depending on that, he decides the final release. You can expect those emails coming on Sundays usually. Whenever there is RC created or final version, then there is git tag, signed git tag created in the Git repository. So it's really easy to do stats like about that, that I can have a look what kind of changes have been merged in the time. Okay, so this is mostly how the machinery is rolling, but those changes somehow had to get into sub-maintainers tree and how that works. So as I already said, the development model is heavily based on mailing lists and emails, and changes themselves are sent in the form of patches. Patch in general might be something to fix a problem or implement a new feature. So what the existing development model enforces heavily is that each patch has a single purpose. It should be easy to review, so you, except for some exceptions, because of course, if you are introducing a new driver, then of course you cannot really separate that to really small changes, but you are just adding a new driver as a single patch. But when you are touching an existing code, then you always have to separate that into logical steps, how you are achieving what you would like to implement. So for example, if I want to implement a new algorithm, then I might just do a couple of patches to clean up that area first, just to make the transition from the old algorithm to a new one as clear as possible, so that reviewers can have a look at the change and understand my intention, my assumptions, my thinking, and not only they should be able to understand that, but also somebody reading that code in a couple of years' time.
Well, it's not important to be stable in between the patches only after the end of the patch series.
Yes and no. it's really important that every single particular step in the process is compilable and hopefully doesn't introduce big regressions. For example, what we do rely on heavily, and that's something that Git as a control version system allows, is that if you find that something is broken, then you can use a so-called bisection process. So you have a first a broken or you have a broken state, you find an older version that is not broken, and then you are essentially halving that time period until you hit that first broken commit. So it's really important that the bisection works in itself. So if, for example, halfway through your series, the compilation breaks, then of course you cannot test it during the bisection. So that's really important. The feature that you are currently implementing, if it's practically feasible, then you should be cutting that into logical steps that are themselves correct. Sometimes it's not really possible, because if you are doing a major rework, then you might break something midway, but usually during the process, that's what happens very often. Yeah, so as I said, not only the changes have to be really self-contained and reasonably understandable, but also changelogs are really crux of the development itself. So, for example, on the right-hand side, I've just picked up a random commit from the Linux tree, so that you can see what kind of standard you can expect. So. Starting with a header, which is describing the commit and author of the change and when that happened, then usually the first line is describing a summary of that change. So in this particular case, we can see that this is x86 architecture specific, and it's specific to AMD. AMD chipsets, and it says that something should be printing a warning when, let's say, some features set or feature bits are set. So then you have a patch description, which in this case is just a single paragraph, but in many cases this can be a load of text. And at the tail of the changelog, you have some tags that are standardized. So sign of by is, or the first sign of by in that section is denoted to the author of the change. If you have more sign of bys, then that's essentially describing the path that patch has been managed until it got to the upstream kernel. So in this case, we can see that Ingo Molnar, who is x86 maintainer, has accepted that patch, put his sign of by, so that we know that he was the one who has accepted that. And there's nothing else. So that means that in order to that change to get to upstream kernel, it was merged, not directly applied by Linus. Then we have links. And that refers to the mailing list discussion, so that you can find it later on, have a look, and maybe read through the discussion, so that you can get more background why the change, or whether there was a significant discussion around that change. There's also a fixes tag, which I will cover slightly later, but just that we can see that this is clearly a bug fix, and the author of the change was so nice to the rest of the community that he has identified that this particular fix is for a pre-existing commit and referencing that commit. So, for example, whoever has that commit applied knows that he needs that follow-up fix in order to have a fully functional. So that's back to your question that are breakages acceptable midway? Yes, they are, because they're happening all the time. Yeah, so from this kind of metadata, we can conclude quite a lot of things. We can see who has created that, how that got to the kernel, whether that's a bug fix. We can easily find the discussion that through which that change has been merged. Yeah. We have more metadata to, for example, if somebody has reported a bug, then we are crediting that person by providing reported by. So this is also the way how you can participate in the kernel development, so that you are reporting bugs and you can get a recognition for that. Then we have act by, which is a mean of providing approval to the change. So for example, if me as a maintainer or co-maintainer is agreeing with the particular change, then I just send as a reply to that email, act by Michal Hocko, and that gives a signal to other maintainers that I do agree with that. We also have a negative thing that it's called neg by, which is a strong disagreement with something, and such a change should never get merged, because we do rely on each other's judgment call, and that usually means that the change has to be re-implemented in a different way. Then we have reviewed by, which is very similar to act by, but essentially has a stronger meaning that not only I do agree with that change, but I have done a throughout review, for example, sometimes have done a lot of testing, and that means that I really believe that the change as is implemented properly and in a way that is acceptable, complying with all the standards. We have already discussed fixes and link and how the actual change is implemented. We have seen that the change log is a simple text, but how can you judge that change itself? So we are using unified diff format, which is a very simple text-based format that describes changes in a text, essentially, in general. So you can see that on the right-hand side, and it describes what kind of file has been updated, and plus, minus to describe what will be removed on what will be added. So in this case, you can see that a function that I have no idea what it does, but it probably can return, or it will very likely return negative number when there is an error, and 0 or positive number when there is a success. So this particular fix is not warning if that function returns anything non-zero, but it should be warning only if it returns an error code, which is a negative number. So you can, even if you are not very familiar with this particular code, you can tell what's happening. So we know that this is a function that is called init AMD, which is probably something that it's called during early boot when the platform is initialized, and the particular code is throwing a warning when something unexpected happens, and that was wrong because it was the condition was not correct. Unlike many other things, I would recommend reading documentation about, or especially documentation process part of the documentation is really up to date and something that you can learn a lot, especially if you want to send patches. Okay, so let's say that you already have your particular change ready, how to move on. So you have to post the patch. And as you can imagine, if you just post the patch to a generic mailing list, it might just fall through cracks and nobody will notice that. So it's really important to find proper people that will pay attention and people who can help to get that merged. We have a couple of scripts for that, most notably get maintainer parascript, which essentially looks in that area that you are touching and looks who has changed that area in the past. Also, there is a maintainers file which is describing different parts of the kernel and who is maintainer, who is or what kind of mailing lists are used for that subsystem, and essentially throws a list of mailing list and people who you should be addressing that change if you want to get it merged. Sometimes it's really good to do a local research yourself. For example, if you're touching a very busy file, then you might get a list of unreasonable long list of people who to involve, and that's probably not a great thing to do. So in those cases, you really want to have a look and identify the most active developers in that area and add them. If there are more people to be added, that can always happen later on the mailing list. Once you have posted that page, and there are a couple of things that you should or should not do. So the first thing is be patient. You can imagine that with those 11,000 patches merged, each merge window, the development is kind of busy. That's happening every 7 weeks or 9 weeks, that such an immense amount of changes is merged. So you can imagine that maintainers are really busy people. It's also very important to listen to the review feedback. You might be really convinced that your particular implementation is the best one on the world, but sometimes the best or the most clever way is not the one that will be accepted, because of course the kernels in general are highly optimized piece of code, but also maintainability is a very important aspect of the code, so that clever code tends to be really hard to follow, hard to understand, easy to get wrong, or much harder to make any changes later on. So it might really, or it very often happens that the first feedback you get from maintainers is that they need to understand better why you are making that change. So please explain why, because then you can converge into a real solution. And the second thing you might hear is that, okay, but this is not acceptable way to implement that thing. You should be doing this and that. Or you might just get a mostly stylistic hints to do something slightly differently, but the essence of the change stays. So be prepared that this is an iterative process. You might be setting version 1, version 2, version 5. It's usually good to denote that what you are proposing is still something that you are not sure yourself about. And we have RFC, a prefix for those patches, so that people know that, okay, we are still trying to figure out what's happening. Last but not least, once the patch has been accepted to maintainers tree, be responsive if there are any follow-up questions. Because if you cannot stand by your change or provide fix-ups, then it's very likely that your patch or your change will get reverted. Yeah, so that's mostly about how the upstream works. So people are signing patches, maintainers are reviewing patches, then they're merging that. It gets to Linux eventually, and then it's part of the released kernel. Now we have downstream kernels, and why would we even want to have something like that? So why is not everybody using Linux 3? Answers are really different, but one of them is the constant evolution of the upstream kernel, which is really hard to get up with, because you can imagine that if you have a let's say your business running on Linux, and if you were to redeploy a completely new kernel every 9 weeks, then and you have to go through testing, then this might be just too fragile for your specific use case. So that's why we have downstream kernels, and I would just mention a couple of those. So there are stable trees, which are maintaining older kernel versions and applying only fixes, so no new features. Then we have community distribution trees. Then we have enterprise distribution trees, and also we have device-specific trees. For example, most of you very likely have an Android phone, and you can imagine that that one is running Linux, and with very specific hardware that it's usually part of only a couple of specific Android models, so they need drivers that are not part of the upstream Linux kernel. So stable trees. Stable trees are officially maintained at the same location as Linux tree on kernel.org, and they are maintaining Git as well. And usually they're tracking two last major releases. So we have just 6.11 has been discontinued, but there are also long-term supported kernels, and you can see some of them are going quite into the past. They are usually collecting fixes proactively, so they are relying on the fixes stack that we have mentioned earlier. Also, you can explicitly mark a patch for stable by cc stable. But one thing that it's worth mentioning is that the support for those kernels is best effort. So if there is a problem, then more likely the culprit of that problem is reverted, then you find upstream developers working on that problem on top of stable tree. Why would you want to use stable trees if the support is only best effort and you are not getting any guarantees? The first and probably most obvious is that it's free, so you do not have to pay for that. And it's a safer option than doing that on your own. Being an expert in the whole kernel is an immense task. So it's better that somebody from the community is maintaining that kernel for you. A slight disadvantage is that the stable process is deliberately designed to not bother upstream developers. So a lot of those backports that are applying those fixes, we call that backports, is not reviewed. So those trees are heavily relying on their users to test that and report problems they're seeing. And I've just added a couple of numbers just to give you an idea how many of those fixes have been backported to stable tree. For example, 6.11, which is really recent, just released recently. So it has already released 11 minor releases of the stable tree and merged something like 3,000 patches, which is quite a lot. And if you look in an older 5.4 based stable kernel, then you can see that there have been released more than 200 minor releases with something like 28,000 patches backported. So a risk of regression with that amount of patches that do not go through deep review process might be quite large, but practically speaking, there are still users of those trees, so it must be working at least for somebody. I would like to also mention that a kernel CVEs, which is referring to security vulnerabilities, is based on stable tree workflow, but I'm not going to go into details about that. If you are interested, I can, of course, but I would like to focus on other stuff as well. Yeah, so other representative of downstream kernels are distribution kernels. Just to mention a couple, there are many. Arch Linux, Debian, Fedora, Gentoo, Ubuntu, or OpenSUSE. Most of them are based on stable kernels. And their added value is that they are, in most cases, except for Gentoo, which is source-based distribution, all others are providing binary kernels, so you do not have to compile the kernel yourself. And much more importantly, you do not have to configure your kernel yourself. So those distributions are just making sure that they are compiling most of the useful features into that kernel, so that users simply download a package, install that in their distribution, and have a fully functional system. Many of them even provide some basic support model. So you can file a bug that community might be trying to invest time and debug or even provide fix for. Yeah, the last category that I will focus on is enterprise distribution kernels, and those are very similar to distribution kernels or community distribution kernels, but they are providing a support model that it's not best effort only. So probably the biggest representatives are Red Hat with their Red Hat Enterprise Linux, Oracle, or SELE, which is SUSE Linux Enterprise Kernel, which I will cover because that's what my bread and butter is. So what kind of support you can expect, for example, for SLE kernels? If you have a workload and that doesn't perform as you would like to, or you can see a regression, or feature doesn't work as you expect, or you would like to have a longer support than the distribution or community kernel provide, for example, you know that you will need 10+ year support model. That's what enterprise kernels provide. Also, they are providing a guarantee of security fixes coverage, all that with some SLAs. Let's say that you are guaranteed that important security bugs are fixed and released within 30 days of since they were discovered or reported. And another very notable thing they are providing is official certifications. So, for example, if you are running critical business, or if you are in touch with certain government agencies, then you are obliged to comply with certain certifications. For example, for security, that would be FIPS. And that's, for one thing, not a cheap process to go through. And also that has a hard requirements on the how you are developing or how you are maintaining your code, and you are not going to get that for community-based kernels. Of course, for those enterprise, as the name suggests, you have to pay for, and that's not cheap, especially if you are looking into 10+ years of support. Then this is not really cheap, but it gets a lot of people to keep that rolling, especially for long-term supported kernels. Just to give you a very brief idea, SUSE Linux enterprise kernels are usually have a major release, and then regularly every 2 years we are releasing service specs which are providing additional functionality. Just as an example, how old or how long a support you can get. I just happen to be an internal maintainer of SLE 11 SP4 LTSS kernel, which has been released 2011. So, and we're still maintaining that kernel. We are still providing bug fixes for that kernel, and sometimes it's not fun. You can imagine, for example, a couple of years back, we've had a major discovery of side channel attacks on Intel architecture platforms, Spectre and Meltdown, and backporting fixes for those issues into such an old kernel was nerve-wracking and time-consuming. But this is something that we guarantee to our customers, so that's something that we have to deal with. So it's not really an easy task to provide enterprise grade support without having manpower behind that. Another really interesting aspect of having enterprise kernels is that in the upstream community, the life is easy. If somebody wants to run a code that it's not part of the Linux kernel, then they are on their own. But you can imagine that there are many people who really want to use a particular driver or feature that it's not part of the Linux kernel. For example, NVIDIA driver that it's not part of upstream kernel because of many reasons. But you would like to use your hardware, so that means that you have to use an out-of-tree kernel module to support that hardware. And in order to do that, and with the upstream development model, which doesn't really guarantee any internal APIs to kernel modules because all supported kernel modules are part of that repository, so they do not have to have any binary interface compatibility requirements. But this is not the case for enterprise kernels, where we are guaranteeing that if you compile your driver against a service spec, then any update that you are receiving will your drivers will still be loadable and work properly. And that's surprisingly, or maybe not surprisingly, not an easy task to do. Yeah, I've just mentioned a couple of certifications. Like common criteria is really notable here because that is not an easy certification process to get through. You have to guarantee many things from all the supply chain security or so. High level of security on premises where you're doing the development. You have to guarantee that nobody can tamper with your code on the path from the development up to and reaching customers, and many customers are really relying on that. Yes.
If you have to do some changes, some bug fixes, do you have to do this process of certification, tests, and stuff like this every time you do some slight changes? Or...
Yeah, so the question was whether any single change that we do to our products need to go through recertification again, and no. And that the reason for that is that part of those certifications is a guarantee that changes that we apply will not break assumptions and requirements that have been certified earlier on. Yeah, so this is just a example of how SLE 15, so SUSE Linux Enterprise 15 family releases have been going through time, and we're just joking that this is a plan until end of 32-bit time, which will happen at 2038, because at that time the 32-bit time will wrap around and get us back to 1970s. So SLE 15 that has started with the first kernel SP0 in 2018, there will be continuity until 2037. So after a year of a general support, there is LTSS support, which means that there is prolonged long-term support. I will say more details about that later on, but you can also see that SP7 that will be released next year will have extraordinary support, general support until 31. So you can imagine that that requires heavy investment into people who are supporting that. If I just look at that 31, I will be almost 50 at that time. So now, how the overall development model of those enterprise kernel is done. I do expect that this will be very similar in other enterprise kernels, but I do not have first touch experience, so this will be less specific. So initially, we are collecting feature requests by our customers and partners, and you can imagine that those partners will be companies like IBM, Intel, AMD, NVIDIA, essentially anybody you can imagine. And one thing that is really notable is that those partners and customers very often are not only using SLES, but they are also using Red Hat because they would like to have, let's say, redundancy in case something goes wrong, because their workloads are really business critical for them. So initially, we are just collecting features. We are using Jira tool for tracking that. Depending on how many features we have, the nature of those features, then we consider what is the ideal base kernel for that. So we are always using Linux 3 as a base, we use so-called TikTok model. So some service specs are changing the base kernel. Some of them are using the previous base kernel and build on top of that. So we have smaller service specs and larger service specs. And sometimes when we just realize that we need to backport something like 50,000 patches, then it makes sense to do rebase. In order to be able to pick a proper kernel, we have a lot of internal testing that is happening while there is development happening. So we have an internal overview which major Linux releases are better for performance point of view or from the feature set. So this is what it's happening all the time in the background. So after we have the base kernel selected or that we stay with the previous base kernel, then we start backporting those patches that are required for feature requests that that our customers have reported. Many times, as I'll cover our kernel teams later on, but we have something like 80 kernel developers that are participating in the kernel development upstream. So they have a good overview of what's happening there. And sometimes we are just proactively backporting stuff that we consider important or people might find relevant later on. And especially if you just realize that that kernel will be maintained until 31, that's really important to have some outlook. So, for example, critical subsystems are getting many more patches than they are required by customers. Our kernels, enterprise kernels, even though that you have to pay for them in order to get a full support, they are generally available at GitHub, so you can just go there and see what kind of code is in our trees, and we're really transparent about that, and we find that really important, not only from the trustworthiness point of view, but also for transparency. Once we are collecting all those changes, then we are releasing a couple of beta releases. Not only we are talking about enterprise kernel, but we are talking about the whole enterprise distribution. So that means that everything has to be put together. User space packages as well. So this is not only about the kernel. I'm just talking about the kernel, but there's really much more happening. At RC1 time, so when we have passed that initial testing, then we are freezing, so-called freezing KABI, which means that at that time, we are promising to not do any changes that might break module compatibility later on. Once we go through all the RCs, then we release a so-called gold master, which is the enterprise distribution release. After that time, we are collecting bug fixes, less so feature requests, but mostly bug fixes, and release them on a monthly basis through maintenance updates. And the bar is really high for those changes to be released for the certification point of view. And once a general support is done, then we are releasing long-term support kernels and products, and those are really conservative. That means that if there is a non-trivial risk that a even fix might introduce a regression, then we are not releasing that. For security fixes, we are focusing on those that have high impact rather than probably very low impact and low probability of being exploited, or that exploit doesn't really compromise the system. as you can imagine, our process has to be rather optimized for and scale, because if we're talking about a kernel tree that has 30,000 patches backported, then and still that whole thing should hold together and make sense, then you should be really organized. So we do maintain our kernels slightly differently than the upstream kernel does, which has a source code, and you are making changes to that source code. Our approach is different, and we have essentially a base kernel that is based on Linux tree, as I've said, and then we are maintaining all those changes that we are backporting in the form of patch files. So if you open our Git tree, then you will not see a kernel source tree, but you will see a lot of files that will get applied on top of that Linux tree. Yeah, in order to have an overview about or why we have decided to backport those patches, we have certain rules on how that patch file should be looking like. So they're usually part of or generated by git format patch command. And we are adding custom tags to those patch files, like git commit, which is referencing the upstream commit. Then we have references to Bugzilla, or for example, in this particular case, this is a security fix which with a CVE number. And also we are recording who has backported that change, so that we can we know who should be contacted in case of, for example, regression. In, let's say, early days, yeah, I'm with SUSE for last 17 years, and initially when we were much more eager to have changes that were not part of the upstream kernel. And one thing that we have learned hard way is that this is almost always a bad idea. Because once you provide a functionality to your partners or customers, they rely on those. And if that feature is not part of the upstream kernel, then you have to maintain that effectively forever. So that's something that I have mentioned earlier, that downstreams are heavily motivated to contribute back to the upstream. And in early days, it was not that we would be not willing to do that, but let's say that there were features which were too controversial to be merged in the upstream kernel in early days, and we were essentially forced to provide that functionality because people were asking for that. Since we have learned, we have employed a upstream first policy. That means that if somebody requests a feature from us, we insist that that feature has to be acceptable, if not accepted by the upstream community. There are certainly some exceptions to, but they are really much more rare than they used to be. And we're definitely not repeating those mistakes from the past where we were providing user visible interfaces anymore. Now, we have those many patch files that should be applied. So how do we apply them so that the result is always the same? We have a serious.conf file, which is listing those files, and they're applied in the order they are put into that file. Most of them are sorted by Git order. So if those patches are not yet part of the upstream kernel, then they are in dedicated sections, or when ordering is particularly not practical. Now you can see that, for example, in SLE 15 SP6, which has been released just last year, we already have something like 28,000 patches backported. We have, of course, we have scripts that you will need to use if you want to expand our enterprise trees into source code that you can compile or look at. So I've just mentioned that sequence patch that is doing that thing. Also, if you just want to prepare something that you can throw at build service to give you RPM back, then there is another scripts for that. Besides the feature that are part of the regular development model, we also are doing a lot of proactive fixing, and that means that we have a infrastructure that is watching patches that are merged in Linux tree, and if we can identify them as being a bug fixes, then we are sending that to our maintainers and experts in that specific area. They are reviewing that, and if they are and if that fix is or that bug fix is safe to be added, then they are reporting that proactively, even without any customers requesting that. But of course, we also have support teams ranging from L1 until L3 that are accepting requests by customers, and that's also part of our daily job to deal with those. Yeah, so those are reactive fixes, and a typical workflow is that, okay, so we have a customer that is encountering a problem. They're paying to be listened by our support teams, and if the support team cannot really deal with the problem that that is reported, then they are escalating that, and that might land on my table as a developer that I need to deal with. After we have a fix, and that might be either something that we find out is already ready in the Linux tree, then we provide a backport. Or if we have to develop a new fix, then we are contacting upstream developers, providing our fix, going through review process, and after that review process is done, then we are offering that to our customers. In order to reduce a risk for that customer to apply something that didn't get through the whole QA phase, that we have something that we call PTF, which is package temporary fix, and that means that they are getting the latest maintenance update with a single fix for a particular problem. So they are not getting regressions, because QA is usually happening before we are doing the release.
We have a question.
Yeah.
On the turnover in the upstream tree, how long does it take?
It really depends. Sometimes it might be really easy because that fix is not particularly complex. Sometimes it can get really frustratingly long. Yeah, if it takes weeks, yeah, it might take months, especially if there is disagreement on a particular way to address that problem. Because let's say that you have something that only a single workload is hitting, nobody else is able to reproduce because that particular workload is so specific, then this can get really complex and long. Yeah. And of course, we are proactively fixing security vulnerabilities, and yeah, and for that, I would just mention that the process for security fixes reporting has changed in the upstream community early this year. And while previously it was mostly based on external reporters reporting a security problem, now it's much more reactive. So essentially, anything that it's pattern matching certain certain characteristics is getting a CVE. And that means that somebody from our teams has to review that. And yeah, for example, previous years we were getting something like 100 CVEs a year. Now we are at more than 5,000. And this means that as we are obliged to provide those fixes or evaluate them as not being important enough, that means that we are quite busy with that. So I've just, in 15 SP6, which is relatively fresh kernel, we have more than 3,000 CVEs backported since the beginning of the year. As you can imagine, that's something that it's not really scaling all that easy, and especially when you have kernels ranging from 3.0 that it's 13 years old up until very recently released SLE kernels that just to find out which code streams needs to get a fix is not an easy task. So we had to invest in our tooling to give us that kind of overview, and yeah, well, let's put it this way: it's a lot of work. Yeah. So who we are as kernel developers at SUSE. So we have roughly 80 people. And most of us are not only working internally on SLE kernels and SLE products, so we are participating in upstream community as contributors and maintainers. So just to mention memory management, x86 architecture, we have IOMMU maintainers, we have live patching developers who are working on possibility to apply changes to the kernel without a reboot, and many other areas. So I've just listed kernel teams that we have. Hardware enablement team, as the name suggests, they are focusing on drivers and support of a new hardware. I'm team lead of the core kernel team, which is mostly focusing on memory management, x86 architecture, S390 architecture, or PowerPC. The other core kernel team, which used to be a single team, but as we were growing, then we just, in order to make that manageable, we have split that. It's also taking care of live patching, kernel live patching. Then we have file system teams who are taking care of mostly Btrfs, but also XFS, or then we have performance team, who those people are constantly running tests, and also they are developing performance related fixes as they are encountering them while they're doing the testing. So it's not only running tests, but also investigating regressions and providing those fixes to upstream. Storage and networking team take care of the IO path, which means storage technologies and networking technologies, and also virtualization team, mostly doing development of XAN and KVM. Yeah, so that was a very condensed, very compressed kind of look into how development work, not only in the upstream as a community, but also in downstream as something that you do for your living. Probably one thing that I haven't mentioned, and it's not really trivial, is that even though that especially in enterprise world, you have different companies essentially competing for customers. From the development point of view, we are all heavily relying on our cooperation, because there's nobody can do the whole task on their own, and that's really important, a sense of the open source development, not only nature but also level of cooperation. So for example, even though that Red Hat as a company is our direct competitor, developers working for Red Hat are our very good friends, and we are dealing with them in the upstream community very regularly, and without any kind of we want something better than everybody else.
Michal, thank you very much for a very good and very important and interesting presentation. I would like now to open the time for questions. Please feel free to ask.
What is something you wish a normal user would know about this kind of process and the development, or something that you are maybe flabbergasted or just like confused about why people are still not getting about the kernel itself?
That's an interesting question. I don't think that I have ever tried to think about that, but I guess one thing that people usually get wrong is that kernel must be really complicated piece of software, so the bar to enter is really high. And I would strongly disagree with that, because I would just say that any non-trivial software project is complex. But if you are motivated, you can jump into that and have fun. So that's probably one thing that I would mention, that you might hear a lot about how the community is full of all different of trolls and disputes, because that's what gets the best of the news coverage. But I would also mention that in general, cooperation with other upstream developers is a very good experience that made me aware of things that me as somebody finishing a university and working mostly on internal software projects was really eye-opening, that you can collaborate with others and reach the goal by that kind of openness. So that will be probably, not sure whether that's answer for a question, but
Also, or SUSE supports a lot of supports a lot of architectures for specific devices. Is there something particular that stands out for you, like a special device that you wouldn't have thought that you actually need to support, and you do?
We are not supporting that many special devices themselves, but what would probably stand out, and something that I have heard for the first time when I joined SUSE, was probably S390 architecture, that usually room size hardware, that there were rumors that, for example, in Nuremberg office, we've had one of those machines that you cannot really buy. You only get that as you just lease that from IBM, and when they tried to turn it off, it just called for a serviceman that something is happening to the machine. It was still running. So that was kind of hardware that I thought doesn't exist. So that would be.
Actually, if I might answer that question as well, because I worked in the data center for a while. I babysat those two big mainframe machines. I don't think that's even the weirdest hardware that we have. Until very recently, we supported and still have in our data center titanium machine.
Yeah.
So IA64 architecture, because we had customers who are still running some, I don't know, banking or telecom or whatever application on titanium, and they're very happy with it. And so we need to build for those customers certain backports for titanium, right? That's I think the weirdest.
Yeah, and probably not all that weird, but it's not really well known history fact that the first 64-bit support for Intel architecture was actually developed by SUSE people in cooperation with AMD. So they didn't really have hardware to develop on, so they they used to do that all in simulators with the final code on the CD delivered to the first machine and try to boot it, and it did. So, so that's not that much of fringe hardware these days, of course, but was not always the case. Most of the kernel is written in C, yes. There is some push for having a Rust support for new drivers, and that's still kind of in baby steps kind of state.
It is not written in C. What is written in?
Assembly language. Let's say that tooling, put aside the tooling, which might be Perl, Shell, and whatnot. A surprisingly large part of that is written in preprocessor, which I wouldn't call it's part of the C language, but I wouldn't call it a C, and you would be surprised how many weird constructs are hidden in macros and preprocessor. And in the future, we can see much more of Rust, especially in driver's land.
I have myself two questions. Maybe one is not my question, but it's a typical question of those days. Why don't you apply any artificial intelligence to this? I know the answer, but...
Yeah, I think that people are trying, mostly to evaluate problems, to find common mistakes, to find common bugs. And for that, artificial intelligence can be really powerful. I'm not yet convinced I would trust AI to write a code that would be running on my machine yet, but maybe we'll grow into that eventually. So I can imagine that some AI-assisted development model will become very really common in the future. So what we should be really careful about is to do a proper and throughout review for those changes. So we shouldn't really let AI write a code that AI is reviewing, because that might just end up in a very bad loops of self-confidence of a completely broken code. But as you have seen, it's natural to break stuff in upstream development model, which is natural because it's mostly evolutionary kind of approach to the development. So if you break something, it's not the end of the world, because you are going to fix that or revert that. So people are making mistakes as well. So arguing that we don't want to have AI because it might break stuff would be just not recognizing our own mistakes happening.
Thanks. And the second question is kind of semi-personal. How do you manage your time? I mean, can you afford like 1 week vacations?
Yes, sure. Yeah,
Okay.
yeah.
Because it looks like you are always resolving something, and it's very difficult for people like you to have a backup if you...
Yes, and this is even much more important in the upstream community, where you have, let's say you have areas where you only have one or handful of people who are familiar with that area, and you can imagine the bus factor is kind of problem. So what we are trying to do in that regard is that we try to pull new people into the development, and it gets harder and harder because at my time, when I was finishing university, sometimes 2007, working on operating systems was something that was a high profile job profile, essentially. These days, it's really hard to find new talent coming out from university. So that's why I'm really happy that that operating systems are still the thing at a university level, because everybody's AI these days, and we were through times where everybody wanted to do graphics and games, and not much left for people who want to do a low-level programming. So, yeah.
To get to the kernel development, did you just said someday like I would develop Linux kernels, or did you read on the internet? How did you get into that?
Yeah, as many people at the time, Linux, or I've started using Linux at university, and it was really exciting to have an opportunity to look into the code that you're running and potentially modify that and, for example, break something. But at my times, you had your personal computer with Windows 3.19, with XP being the fresh new thing, and that really didn't attract me. So I started using Linux, and sooner or later I just came across the Linux kernel, which was said to be a high demanding, high quality piece of code. So I started looking into that, and then at university I was doing my master's thesis as an extension to memory management. And shortly after I finished, I was just kind of lucky to enter SUSE and start working on that. First as an L3 engineer, seeing what kind of or how customers can use Linux in really mission critical situations, and that attracted me even more. And then I just turned that into my not only hobby but also paycheck kind of.
That was your first and your only job.
I used to work in other companies previously during the university studies, and that was hugely closed source, internal projects, stuff that, quite honestly, I was not really entirely thrilled about in the end. That's not really easy thing to get to usually, but build testing to cover all sorts of different combination of configurations is usually applied without even you asking for that. Yeah, thank you for having me.
Course, it was area, and I'm sure that we will have a chance to cooperate closely with Michal and SUSE in the future. And if you are interested in any more details about the topics that Michal mentioned, please don't hesitate to contact either myself or Michal, or better through myself.
Yeah.
Maybe Tony.
Also, I am the university coordinator for SUSE, so I kind of manage opportunities for students and research opportunities and such. And there are even possibilities to do a bachelor's or master's thesis potentially on some topics.
Yes, well, this, yes.
And if you are, good there, or if you feel you're a really strong programmer, we have an engineering training program that we're going to be implementing, where you can visit various teams, not just the kernel development teams, but other teams that help make all that work in the background, QA teams, and others. So SUSE.com/university is one way, or you can write an email to universities@SUSE.com, and I read all of them. So.
Yeah, we have some experience with leading master's thesis. Some of them was done at Mathis. I was not involved in all of that, all of those activities, but let's say that if you have an idea or concept of an idea and you would like somebody to help you pursue that, certainly we can talk. Okay, so thank you for your attention.
Yeah, I think most cooperation in Czech Technical University and SUSE, and to provide them some interesting topics.
Thank you.
Yeah.
Okay, tak já mám